Instead of doing questions at the beginning, I want to make sure we get through what we need to get through first. So we'll go through any questions towards the end of the period. And then if there's any questions that you still have that I don't get to, tell me what they are, and then I can do a little screencast video of a solution and put it in D2L in the announcements for you. So if there's any that you really want to see before we review Thursday, let me know and I'll do that for you. Should be pretty easy. So the first thing I want to finish off, the last problem we did was the arc length of this cardioid. And I made a comment about that cusp. And that cusp can be problematic when you find arc length. Sometimes it matters, sometimes it doesn't. And what I said was that if you get a goofy answer and you integrated through that cusp, it probably mattered. And so that you should go back and then use symmetry instead and not integrate through the cusp. So sometimes you can integrate right through it and it doesn't matter, sometimes it does. And what I noticed after class was right here, so we tried to just go right through it, and we got an answer that wasn't weird, so I didn't question it. But is this correct right here? When we plug in 2 pi, here we get what? 0. When we plug in 0, we get 0. So then we end up with 1 minus 1, which is 0. So we get an arc length of 0. That's the red, that's the warning signal that, oh, we can't integrate through the cusp because we got something weird. Does everybody understand why this actually is 0? Everyone see that? You evaluate this whole quantity at 2 pi and you get 1. And then you subtract off what you get when you evaluate that quantity at 0. So you get 1 minus 1, which is 0. So that's where it shows up as a problem. So what we have to do then is just use symmetry, and it's very simple. If we look at our picture, the natural way to go is to go from minus pi over 2 to pi over 2 and double it. And so if we do that, all we have to do is convert all of the limits of integration. Now we can leave it as 0 to 2 pi until the end, and we see that, oh, there's a problem. So at the end where there's a problem, what we're going to do is convert it. We're going to say, oh, whoops, problem. We'll go from minus pi over 2 to pi over 2 and double it. So that's the doubling right there so that we get the whole arc length. So is that how you spell double?
Sure. Definitely.
Oh. Okay, so, and then watch what happens. So then we won't get a problem. That's so big now. So then we won't get a problem when we go to the evaluation step here. So out in front, we have 2 times 2. And then here, this is 2 root 2. So we have a total of 8 square root of 2. And then we have to plug in our upper limit. Upper limit, sine of pi over 2 is 1. 1 plus 1 is 2, square root of 2. And then we plug in our lower limit, minus pi over 2. Sine of minus pi over 2 is negative 1. So we get 1 minus 1, which is 0. So that turns into a 0. So here we're going to end up with 8 root 2 times 2, so we get 16. So that is going to be the arc length of that cardioid. So one piece of advice is just don't bother integrating through the cusp because it might matter. And so just use symmetry to be safe. Or if you want to try to integrate through the cusp and figure out when it works and when it doesn't work, then if you end up with a weird answer, just go back and use symmetry. So either way works. So let's try another one.
Would it be an option to integrate from the cusp to the cusp?
You can do things like that, except what's going to happen here, and I haven't figured out exactly, for every cardioid it's a little different. It depends if it's on its side, if it's vertical, if it's upside down. But what you'll notice if you do what you just suggested, if you went from say pi over 2 to 5 pi over 2, you're going to have a similar situation to what we just had. If you do pi over 2 here, sine of pi over 2 is 1. Sine of 5 pi over 2 is also 1. So you're going to end up with 0 again once you take the difference. So that's also not going to work in this case.
Okay.
And I looked in a bunch of other books too to see if there was a pattern, and I haven't figured out exactly what the best pattern is, other than if there's a cusp and you don't get the right answer, use symmetry. Sometimes what you just said will work, but I can't figure out when. And when you look at the condition of the theorem that allows us to do this is this one here, and all they say is that the derivative has to be continuous. And so in this case, in the problem that we just looked at, when we take the derivative of this, the derivative of this is minus 2 cosine of theta. That's a continuous function on the interval that we're integrating over. So there's some subtlety that is a little vague because that doesn't seem to be a strong enough condition. The derivative of r is continuous on the interval from 0 to 2 pi. It's continuous on pi over 2 to 5 pi over 2 also. So the moral of the story is if there's a cusp, it's probably safest just to use symmetry. But if you turn your cardioid on its side, you can integrate right through it and it doesn't matter. So there's definitely some funny business with the cardioid. Definitely funny business with the cardioid. Okay, so let's do, I think it's at the bottom. Let's do one more. So with these polar curves, our goal is to find the arc length of them. We can graph this pretty easily if we use Desmos or some other graphing utility. In this case, it's not going to matter so much. There's not going to be any cuspy things to worry about with this one. So we can just integrate this straight up. And so the ones that I would ask you to find an arc length for in a test would be ones that you could graph really easily. So if I ask you to find this arc length where you can't graph it easily, it means you can just do the thing straight through without worrying. Okay, so you don't have to worry about a cusp or something. So here, let's take our derivative. We're going to get 2 sine of theta divided by 2 multiplied by cosine of theta divided by 2 multiplied by 1/2. Everybody okay with the derivative? Chain rule? So that's just going to simplify to sine theta over 2 cosine theta over 2. And then we can go right to our arc length formula. Arc length formula says integrate on the interval. Tell me if you have trouble with that derivative. I know it's still early in the semester, chain rule. And we have to integrate r squared plus r prime squared. So r squared turns into, and a square root, r squared turns into sine to the 4th of theta halves. R prime squared turns into sine squared theta halves, cosine squared theta halves, d theta. And here we can factor outside of the square root. We can pull out one factor of sine theta over 2. And we can do that because we're factoring out sine squared and the square root of sine squared. When you're on the interval 0 to pi, sine is non-negative, so you're allowed to take the square root of sine squared and get sine. So that's important that the interval is an interval on which sine is positive. So that factors out. And then aren't we left with just 1? Aren't we left with sine squared of theta over 2 plus cosine squared? Theta over 2? d theta? So that whole quantity right there is equal to 1. And that is integrable. The integral of sine is minus cosine. Theta divided by 2 Reverse chain rule says we have to take the derivative of the angle and then divide by that. So dividing by 1/2 means multiplying by 2. Then we have our limits of integration. So that gives -2 cosine of pi over 2, 0, and then subtract off cosine of 0, which is 1, so we end up with 2.
Thanks here.
So that will be our arc length. So if you're given an arc length problem and it's not one that you can draw easily and think about, oh, is there a cusp I have to worry about, then just don't worry about it. Just go ahead and do it. Any question on any step? Good? Yeah?
Yeah, just curious. This graph would probably be like a circle with origin several points below, several units below the
So this is a polar curve, so it's, you know, so it's a little different than a trig function graphed on the Cartesian plane.
Yeah. Although pretty much this would kind of graph circle pretty much.
I don't know. We can type it in and look during the break. You just have to type it into Desmos, and it will graph it pretty easily. I don't think it'll be a circle, though.
Shouldn't it be more like a flower type thing?
I would imagine it's,
Or like a wiggly circle?
typically, it could be like a bumpy circle. But the flowers and roses usually have this form here, where you have one trig function like that, not a square. So depending on, and then you might have a multiplier in front of there, actually. For the roses, you will have something in here, so some other constant in there. Yeah, so, but you can graph it and see. It's not one that we would be expected to know. Okay, let's get to this whole arc length mumbo jumbo. So, first off, right here we have the arc length function. So we have to distinguish between the arc length formula and the arc length function. Do you see the difference? So the arc length formula that we've been using, the arc length formula has constants right here, and then we integrate, normally we write it as r prime of t dt with absolute value bars around it. So this is the arc length formula. Does everybody see the difference? So with the arc length formula, you end up with a number. You end up with a numerical value as the answer. This letter here, the t, is just the dummy variable that allows us to integrate, and then it disappears once we plug in the a and the b. So the arc length formula is giving us a numerical value for the arc length. But notice this. This is an arc length function. This is telling us what the arc length is from a to t. So here, u is the dummy variable. And if you were to integrate this and plug in your limits of integration, you would end up with a function of t. So it's going to give you the distance from point A on the curve to whatever you plug in for your t value. So it's a function. It depends on what you plug in for t. So that's the arc length function. We still are integrating speed. Whether you write speed as r prime or v, it doesn't matter. So you integrate speed to get length. Now, if this is true, if the magnitude of the speed is 1, then we say that we have an arc length parametrization. If the speed of the curve is 1, we have an arc length parametrization. So all that means is for every unit increase in the parameter, you've taken 1 unit of length, one step on the curve. So if the speed is 1, it just means that every time the parameter increases by 1, you've moved 1 unit further along the curve. As opposed to a lot of the curves where you move 1, you type in you test, say, t equals 3, and you're somewhere on the curve, then you test t equals 4, and you're much further than 1 unit away from where you were at t equals 3. So with a general parameter, you don't have that situation where a unit increase in the parameter gives you a unit increase in length. So with an arc length parameter, it's tied. If you increase the parameter by 1, then you've increased the arc length by 1. So we'll see how that all works out. All right. So definition here. So a curve is smooth if the derivative exists in the entire interval and r prime is not 0 for any t in there. So this is important because with a parametrized curve, you can't always see points where the curve is not differentiable. When you are in Calc 1, if you look at a graph and you see a cusp, you say, oh, not differentiable there. You can't hide a point of non-differentiability. You see the cusp. Okay, you see those vertical tangents, right? If you have a circle, you have the vertical tangents, so it's not differentiable at those endpoints. With a parametrized curve, it's not always the case that you can see it graphically. And the reason is that as the parameter increases, it's possible to go up a curve and then come right back down the same curve. So the graph might have a hidden corner because you've gone up it and then come back down it. So you can't rely on looking at the graph. So what this condition here says, r prime not being 0, that prohibits the curve graphing from stopping and turning around. Okay, so for it to be smooth, we have to have the derivative existing, and we can't have any stopping. As soon as you get a velocity of 0, it means, uh-oh, then we're not going to call it smooth because you could be turning around and you could have a hidden cusp. So definition for smooth, derivative exists, and non-zero. All right, so let's deal with this problem first. Determine whether the following curves use arc length as a parameter. If not, find a description that does use arc length as a parameter. So if we have a curve, and we want to know if it's parametrized according to arc length, we just have to test the velocity. And if the velocity has unit speed, then it's an arc length parametrization. So in a lot of classes, upper level classes, they'll call an arc length parametrization a unit speed curve. So let's see if we have a unit speed curve. So for a unit speed curve, we check our velocity. So here's our velocity vector. We see that our velocity vector is constant. Now let's check its magnitude to find the speed. So the speed is the length of the velocity vector. We'll take the square root of the sum of the squares. We get 1. So therefore, R is a unit speed curve. And that just means that it's parametrized according to arc length. So that means if you increase, so if you imagine the graph of this line, and you go from t equals 3 to t equals 4, the distance along the curve will be 1 unit. If you go from t equals 7 to t equals 8, the distance along the curve will be 1 unit. So an increase in 1 with the parameter corresponds to an increase in length by 1 on the curve. That's all it means, unit speed curve. Now let's test this one. So this is a curve in 3-dimensional space. Same question, is it a unit speed curve? Is that parameter corresponding to arc length or not? So we'll find the velocity. And once we find the velocity, then we'll figure out what the speed of the curve is by finding the length of the velocity vector. So there is our velocity vector. So we're imagining this curve in 3-dimensional space. That derivative vector, that velocity, you imagine as little tangent vectors along the curve in 3 space. And then this tells us our speed. So we'll do the square root of the sum of the squares. And what we see is that we definitely don't have a unit speed curve. When we combine our like terms in here, we're going to end up with 25 sine squared plus 25 cosine squared So the sine squared plus cosine squared turns into 1. Square root of 25 is 5. So that's the speed of this curve. So that says if you, and it's a constant speed, so that says if you increase the parameter value by 1, so you look on the curve at t equals 1 and t equals 2, the distance between them is 5. That's what that means. So that means that we're going 5 units along the curve per 1 unit increase in the parameter. All right, so not a unit speed curve. So then it says, well, convert it to a unit speed curve.
You just divide by 5.
Divide everything by 5. So here's how we would do it formally. So the idea is that here we have a curve with a parameter of t, and we want to convert it to an s. So I'm going to do this. I'm going to use the arc length function. And the arc length function is going to tell me how s and t are related, and we just saw how they are related, but let's just go through the full all the steps. So we're going to put in the 5 du, and this ends up being 5t. So this tells us that t is equal to s divided by 5. So that arc length function gives us the connection between s and t. So we integrate the speed. We found the speed to be constant of 5, and we had this intuition that, oh yeah, if we divide by 5, we should get a unit speed curve. So here's the formal math for it. We go to our arc length function. We integrate speed on the interval 0 to t, and I'm starting at 0 because that's where this interval starts. That's why that's a 0. And then we go up to t. We integrate the constant speed. Well, we get 5t. So now we have an equation. S equals 5t. Divide both sides by 5, and that tells us how to replace t to get a unit speed curve. So now we go back to our original curve, and we're going to rewrite it as r of s. If you write it as r of s, that means that you've parameterized it according to arc length. So it's kind of understood that if you do use an s, that it's a unit speed curve. So we go to all of our t's and replace them with s over 5. So that should be a unit speed curve now. And what would the interval be? So s is going to come from the interval. So we go back up to the t interval. When t is 0, s is 0. And when t is, what was the ultimate endpoint? Was it pi? So we're replacing t with s over 5, so it's going to go from 0 to 5 pi.
My s's look way too much like 5s to do this problem.
Yeah, s's, 5s, yeah, very dangerous. So how would we double check that we did it right? What should the magnitude of the velocity be for that? 1. So we just take the derivative. Let's just test it just to make sure that we didn't make a mistake. So we're going to get negative 5 sine of s divided by 5 divided by 1/5. So that means multiply by 5. I'll just put a divided by 1/5 like that, just for the heck of it. And then derivative here is going to be 3 cosine of s divided by 5. Oh, I meant multiply by 1/5. Yeah, sorry. Multiply by 1/5, so I could write that as a division by 5. Multiply that by 1/5. Derivative here, 4 sine, s over 5, multiplied by 1/5. So we get that. And now we take the length of this. Those 5s cancel. Take the length of this. So we get the magnitude of this r prime, and we're going to get 1. Because this will be sine squared. This is going to be 9/25 plus 16/25. Let's see.
The last one should be cosine.
Oh, that's a cosine. Thank you. That's a cosine. Derivative of sine is cosine. So 9/25 plus 16/25, that's 25/25, so we end up with sine squared plus cosine squared, which is 1. So that just confirms for us that it is in fact an arc length parametrization, that we found a unit speed curve. So that is what we were looking for. Any question on any step up there? Yeah?
I'm just curious. I was looking at the arc length formula for curves in polar form.
Mhm.
Why that one seems like it's much more complicated. It's the square root of f prime plus f prime squared.
It's not, well,
Why-
maybe it looks...
why is it so different? I guess I should say.
It's different because of this. So, so when we are using our polar conversions, those are our polar conversions, right? So if we have a polar curve, we usually write them as functions of theta. So let's just suppose we have 2 plus 2 cos. So suppose we have a cardioid. So we have that. Well, you can do two things. You can find your r prime here, and then use the formula, the square root of r squared plus r prime squared.
Okay.
Or you could go back to when we had the parametric form, where we had the square root of x prime squared plus y prime squared. But notice that it's going to be the same thing. When you come down here, you've got to plug this r in for each of these, so that you're going to have x equals 2 plus cosine of theta, 2 plus 2 cosine theta. And you're going to have to multiply this out, and it's going to get pretty messy. So your x coordinate is 2 cosine theta plus 2 cosine squared theta.
So it makes it simpler, even though the formula itself looks more complicated.
Yes. It is actually, in the long run, you are probably going to save time if you use the new formula.
Okay.
Does it matter? No. If you don't want to remember a new formula, then just use this. So the two formulas, you have the square root of x prime squared plus y prime squared. Usually we use a t. I have a theta in there. It doesn't really matter. Or you have L equals the square root of r squared plus r prime squared. So either one is going to give you the same. They're both going to be about the same amount of work. So the polar one that we've been using for the last couple problems may feel like, ooh, it's got a lot more stuff in it. But if you convert it back to dx and dy and use this one, it'd be pretty messy also.
Okay.
So those will give you the same answer, though. I think was that the last problem on that? Oh no, we're on this one. Okay, so let's go ahead and talk about this. This is kind of a review. It's more of an observation than anything. So it says find a parametric description of the line segment. So we talked last time about parametrizing a line, and for a line we have this general rule. For a line we say that r is going to equal vt plus r sub 0. And we say that this v vector, we call that a direction vector for the line. And this is some initial vector. So that initial vector, sometimes we think about that as pointing to the origin of the line that we're creating. But you need those two pieces. You need some direction and you need somewhere to start. And so here they're just giving us a generic situation where we're going to have 2 points. We're going to go from P to Q. So the direction vector then is nothing more than the terminal point minus the initial point. So it is x1 minus x naught, and then y1 minus y naught, and then z1 minus z naught. So that's the direction vector. And then we need to use one of those 2 points for our starting point. And it looks like we're starting there and going to the other one. So we'll start at x naught, y naught, z naught. So our line will be the direction vector times t plus the starting vector, which we'll call x naught, y naught, z naught. And now they said make it a segment. That would be the entire line that passes through those 2 points. If we want to make it a segment, we have to put a restriction on t. And what is the restriction that we will use?
0 less than t, less than equal to t, which is less than equal to 1.
So 0 to 1 will be our interval. And if we write this out in long form here, where we combine our components, they would look like this. Does anybody need an explanation of that 0 to 1 thing? Does everyone remember why it is what it is?
Because it makes it easy.
No, you don't need an explanation?
No, I do need to explain it.
No, yes. So if you take a look, if you plug in t equals 0, plug that t value in down here. So if you plug in t equals 0, doesn't this, and this all wipe out? When you plug in t equals 0 to your parameterization, you end up with the point x naught, y naught, z naught. So at t equals 0, it positions you at the starting point. So it's kind of by construction. Like the way we constructed it is why 0 to 1 will work. And then what happens when you plug in t equals 1? When you plug in t equals 1 down here, then the z naughts go away, so you end up with z1. Do you see that the y naughts disappear and the x naughts disappear when you plug in t equals 1? Everybody see that? So when you're plugging in t equals 1, you're going to end up at the terminal point, x naught, y naught, x1, y1, z1. So you pick 0 to 1 because it works. When you plug in 0, you're at the starting point. When you plug in 1, you're at the end point. That's the terminal point. The one thing to keep in mind, though, is that if you don't use the entire distance from the terminal point to the initial point as the direction vector, then your t interval is not just 0 to 1. All right, so if you are dealing with this situation here, if we suppose that that's p and that's q, if we use that as our direction vector all the way, then definitely t is going to come from the interval 0 to 1. But you could also use a direction vector that's shorter. You could use that direction vector. Let's suppose we use that one, let's call it v star. Well, then we have to count up the number of v stars that get us from one to the other to figure out our interval. So our t star interval would go from 0 to probably 5. So it kind of depends. But if you always find your direction vector by doing terminal point minus initial point, then it's always 0 to 1.
Is there any reason not to do that?
No, normally you would just go 0 to 1. But what we'll see when we get into the project is that there's going to be times where we might want to reparameterize to have an interval of a particular length for some reason, which we'll see.
Okay.
For some reason. We will see. We will see. Any other questions on that one? Whew, what the heck? All right. Cycloid. So this one, has everyone seen the cycloid before? Yeah. Cycloid, you take a wheel or a circle and you just roll it. The cycloid is this curve with these bumps on it, formed by that point on the circle that's rolling. So you roll that circle down the x-axis and you get this curve called the cycloid. And that cycloid's got all sorts of interesting properties. Should we talk about some of those interesting properties? Yeah. So if you take that cycloid and you turn it upside down, The cycloid turns out to be the curve that solves a couple of really, they're kind of important problems back in the day. One of them is called the brachistochrone problem, and one is called the tautochrone problem. And so all that means is that if you take that cycloid and you turn it upside down, like that, if you drop a ball from here, or you drop another ball simultaneously from there, it will reach the bottom at the exact same moment. That the curvature of the cycloid is such that it doesn't matter where you drop the ball. It takes the same exact amount of time to get all the way down. So that is the one curve that has that property, that the speed is constant regardless of where you drop the ball from. That's weird, huh? It's so hard. So hard to imagine. And those guys, who are those guys? Like the, what's his name?
Mythbusters?
Yeah, what's that Mythbusters guy?
Adam Savage.
Adam Savage and
Michael Stevens.
And Michael Stevens, yeah, they do some crazy thing where they build one of these and they kind of do an empirical test to show that
Cool
the
video.
time is, yeah, it's pretty cool.
Vsauce.
Vsauce. Vsauce is the man. Okay, so here it says we've got our parameter 0 to 2 pi. That gives us one lobe of this curve, one arch of the cycloid. Show that the length of one arch of the cycloid is 8a. Let's just set this up. We don't need to go all the way through it. So this one is going to be similar to the old arc length formula, because this one we have a parametrized curve as opposed to a polar curve. So with a polar curve, you have the square root of r squared plus r prime squared. For a parametrized curve, we're looking at this formula, the square root of x prime squared plus y prime squared. Did they use a t? They used the t, 0 to 2 pi. So that's going to find our arc length for us. So we'll go a few steps into it. It's really just a verification. So we're just taking derivatives and squaring them and adding them and doing what they say to do. So the derivative for x prime, we are going to end up with a minus a cosine of t. Derivative of the other piece, derivative of cosine is minus sine, so I think we just end up with a sine t.
Why would we end up, yeah, never mind.
And so then we have to square both of these. So let's go ahead and at least do that. X prime squared. So that's going to end up with a squared minus 2a squared cosine of t plus a squared cosine squared of t. And if we square this one's easy. We get a squared sine squared t.
Just foil that.
Yep, foil. Just foil it out. So then when you add these together, that will give us what's inside the square root. So our arc length is going to be the integral from 0 to 2 pi square root of, adding those together, do you see that you get 2a squared minus 2a squared cosine of t? Because of the combining of this and this. When you combine those two, you get a squared? Yeah?
With the y prime?
Yes.
Where's the first a go?
Oh, did I not take the derivative very well? Is that what you're saying?
Oh, no, I don't know. I'm just asking.
Let's see. Okay, go ahead and ask your question.
Because it was the same thing, like a times 1 minus cosine t, so shouldn't there be like a...
I think we did it okay. So when we multiply this out, we have that y is equal to a minus a cosine t. Derivative of a is 0. Derivative of cosine is minus sine, so we end up with a times sine. This one, when we distribute, we have two functions of t here.
T instead of
Yeah, that makes sense.
Do you see that?
That's what I
Yeah,
did too.
yeah,
That's
so
why
the-
I was about to ask the question.
Yeah, so the second one just doesn't have that extra t in it. All right, so we differentiated right. squared it right.
That was sine squared cosine squared equals 1. That's why you
Yes,
Okay.
exactly. Because right here, when you add these two together, you get a squared multiplied by the quantity sine squared plus cosine squared. So you end up with an a squared. And then a squared plus a squared gives 2a squared. And then 2a squared can come all the way out to the front, so you get square root of 2a times the integral from 0 to 2 pi square root of 1 minus cosine t dt. And let's stop there. We did this one the other day. Took us a while to get our integration hats on, but remember what we did to integrate that? Pardon?
Conjugate.
Yeah, conjugate, exactly. Conjugate madness. So if you multiply this top and bottom by square root of 1 plus cosine of t, that will work. So, yep, that was our trick to integrate that one. And when all is said and done, you're going to end up with 8a. So when you integrate that. But we don't need to go through that integration. Any questions on getting it set up to that point, though? All right. Let's go to this one. So we have a line here, and they're just asking us to confirm. They say, confirm that this condition, a squared plus b squared plus c squared is 1, that is the condition to ensure that this parameterization is an arc length parameterization. That's all they're asking us. And we've kind of learned pretty quickly that to test whether a parameterization is an arc length parameterization, all we have to do is look at the velocity. And the velocity is the derivative of position. And for it to be a unit speed curve, the velocity has to be a constant. It's got to be 1. And that's what we have right there. So the only way that we have a line that is a unit speed curve is if the velocity is 1. So if we're thinking about xy plane type stuff, y equals x, that line has a slope of 1, and that's going to correspond to a unit speed curve. But if we have a line that has a slope other than 1, it's not a unit speed curve. That's kind of what this is dealing with. All right.
Could you scroll back down just for a second?
Yeah, absolutely. Sorry. Jumped off that quickly. Any questions on that? So, one thing that I was thinking about with the, I don't know if I mentioned it. So when you're talking about circles, is it becoming kind of obvious how we would deal with circles? I don't know if we generalized what we did a few minutes ago. So this one, this one's in three-dimensional space, so it's not quite in the category that I'm thinking of. I thought we had one that was just in two-dimensional space. Yeah, maybe we didn't. So if you have a circle of radius 5, let's go to the end here and just take a look. So let's suppose that we have a circle of radius 5. So that would be, the simplest parameterization would be something like this. And we have this pattern that is always going to emerge when we have a circle, that if we take the parameter t and divide it by the length of the circle, we're going to get, I feel like we had one that was this, but Okay, so that's the speed of the circle. And you're going to see this pattern that you can always convert it to a unit speed curve if you just take the radius of the circle and do this division. And so this is always going to work with the circle. You can always just take whatever the radius of the circle is, divide the angle by the radius of the circle, and then you're going to have a unit speed curve. So if you were to take the derivative here, the 5's cancel, and you're going to end up with a speed of 1. So that pattern is just one of those things you want to observe, that when you're dealing with circles, you can just divide the parameter by the magnitude of the radius, and you get a unit speed curve, which should make sense. Haley, question?
It's on my face. So I was just thinking, like, you take the magnitude of that, wouldn't it be 5?
Yep, so we divide that by 5.
Oh.
Divide the...
But didn't you write it as 1?
So now, so to reparameterize it, so this is our arc length parameterization. And to confirm that that is an arc length parameterization, if you take the derivative of this and figure out what the speed is, so r prime of s is going to be minus sine of s over 5, comma, cosine of s over 5, and then the length of this is 1.
Oh. Oh, I thought that was, okay, r prime above.
So this is a new parameterization. So these curves are identical curves. So this curve has the parameter going from 0 to 2 pi. That gives you 1 revolution of a circle of radius 5 centered at the origin. And then this one, what would the relationship be here?
10 pi.
Say again? So we have to get that all the way, we have to make sure we get this all the way up to 2 pi, right? So what's that, 10 pi? So anytime we have a circle, we can convert it to a unit speed curve and stretch the domain. All right, let's go to,
Baseball problem?
you want to do a baseball problem?
Can I do a football one instead?
We can do a football one. You mean the one that we worked on last class? Yes. So let's talk about that one for a minute, because that one is so simple. And so they gave us the accelerate. What does anyone remember what the problem number was? And that one is way easier than I let on.
Okay.
So baseball problem, we have this scenario. So in the baseball problem, they tell us that there's acceleration due to gravity and acceleration due to the spin of the ball as the pitcher throws it. And they told us the acceleration had, what direction was the spin in? The north direction?
So it has the spin of the baseball, horizontal acceleration 5 feet per second squared in the northward direction. It's 3 feet above the home plate.
Okay, that's where it's hit.
Yeah.
So it's hit 3 feet above the home plate, and then it's going to come into the field and land somewhere like that. Somewhere in that first quadrant between east and north. So they're telling us that there's acceleration in the north direction. So when the ball comes off the bat, it's going that direction at 5 feet per second squared. And then there's also gravity pulling down at 32 feet per second squared. So if that's our acceleration, we just integrate twice. And that gives us our position at time t. So, and what was the initial velocity?
30, 30, 80.
So initial velocity is 30, 30, 80. So that tells us when the ball leaves the bat, it gives us the initial velocity vector and the components of that initial velocity vector. So to get velocity, we integrate acceleration, and then v naught, when you integrate acceleration to get your velocity vector, v naught is the constant. So when you integrate this, you get constant. You integrate this, you get 5t. You integrate this, you get minus 32t. And then we add the initial velocity. And so this will be our velocity at time t. So we integrate the velocity, we integrate the acceleration, we add the initial velocity vector. That gives us our velocity at time t. If we integrate again, it gives our position at time t.
And then we have to account for the fact that it's up 3 feet high.
Oh, and when we do the position, good point. So let's do that. Let's make sure we finish this off. So when we want to get our position, we integrate our velocity, and then we have to add the initial position. The initial position is 0, 0, 3, if that's what where we're hitting it. So then when we integrate once again, we get plus 0, and then this one we get minus 16t squared plus 80t plus 3. So that will be our initial position. Excuse me, that will be our position at time t. It has our initial position when you plug in t equals 0, but it has all future positions as t increases. All right, and so then when we want to figure out the time of flight, we just set z equal to 0. Now, if you have a graphing calculator, or if you have Desmos on your phone or whatever on your computer, if you set this equal to 0, you can graph it in Desmos and get your intercept instantly. So that will tell us that t is equal to whatever it is, 5 seconds, 4 seconds, 3.1 seconds. If somebody wants to plug it in and tell me what it is, I'll put it there. Otherwise, I'll just use a symbol. I don't think, does anyone have trouble finding the t-value using either the quadratic formula or your phone or Siri or something?
Wait, Siri can do this for you?
Siri's brilliant.
Cortana's better.
I disagree.
Because
I have
Siri talks to Wolfram Alpha. That's what the math engine behind Siri is. So if you say Siri, factor 5,653,222, it's instant.
It's just like a calculator, but it tells all your information to the
I
NSA.
know. Did you get your t-value, Will?
Yeah, 10 plus square root of 103 all over 4.
Do that as a decimal approximation for me.
Negative 0.0372.
The other one.
Oh, okay, right.
We're not going back in time yet.
Yeah, this thing is this thing is having difficulty
Say again?
figuring out how to approximate what I want.
5.037, so we'll go 5.04 seconds. Okay, so that's the time of flight then. That's when the ball hits the ground, base hit. And then the next question is, okay, what's the distance it travels? So we need to know this distance here. That's the distance it travels, that d. That has nothing to do with the z component. We're just going to look at the right triangle that's formed by the x component and the y component. So what we're going to do is look right here, and our distance traveled will be the square root. It's going to be the hypotenuse of that triangle. So we have to come in here and plug in the 5.04. So 30 times 5.04. And then we've got to square that. And then we've got to plug in the 5.04 to the second component and square that. So 5 halves times 5.04 squared plus 30 times 5.04. All that squared. And that will give us our distance traveled. Does everybody follow that? So the distance traveled, the distance from home plate where it was hit to where it hit the field, is the hypotenuse of this right triangle right there. That right triangle is totally determined by activity in the xy plane. So the hypotenuse is the square root of x squared plus y squared. So there's x, there's y, plug in the 5.04. And then the last question there said, was there another piece to that one?
Max height.
Max height. So to get the max height, we look at the velocity. We want the vertical velocity to be 0. So we set that equal to 0. Get a t-value, and then plug it into this height function, and then that will give us our max height. Everybody follow that? So the max height occurs where the y component of the velocity is 0. We have a horizontal tangent, so the, should I say the y component?
Z.
It's a homer.
So it's a homer, it went over?
344.87 watts.
Oh. What's a homer?
Depends which side of the field you're
Depends on what field.
Dead center.
So you said solve
Okay, so
velocity.
so the velocity, so up here, we want the z component. So the vertical component, the z component's measuring the height, and we want that derivative to be 0. Because at the height of the ball, it has 0 velocity, because it's turning around and coming back down. So we set that equal to 0. So max height minus 32t is equal to 0, minus 32t plus 80 is equal to 0. So t is equal to, what, 30 seconds? 40, 16, what is that? 16 goes into there 5 times and twice. So 2.5 seconds.
Yeah.
And then if we plug that 2.5 seconds in to the up component, so we're going to go to the up component, which is right here. So that max height is going to be minus 16 times 5 halves squared plus 80 times 5 halves plus 3. That'll give us our max height. Because that's measuring the height at time t. So we're just figuring out a particular t value to then compute the height at. So that'll give us our max height.
103.
How much?
103.
103.
That seems too right.
We're dealing with feet, right?
Yeah.
That's not that high. That's no homer.
Does it have to like go up and over?
It's got to go pretty far up to get over.
Just hit
Could be
people
like a
in the
line
car.
drive homer. Just like,
Could be Fenway Park.
not in that way. It's like round one.
All right, so let's go ahead and take our 10-minute break, and then we'll go into 11.9 and deal with curvature. Curvature.
Thank you for doing that.
I'll get that later.
I was trying to hit this trash can.
So the idea with curvature is that we're measuring how quickly a curve is turning. And we talked conceptually about the curvature of a circle being the reciprocal of the radius. So the bigger the circle, the smaller the curvature. Everybody agree with that? Smaller the curvature. Curvature is a positive number, or I guess I should say a non-negative number. A line has curvature equal to 0. All right, so here they're just trying to get us to, here they're trying to get us to see that if we take a look at some points here, so we're going to take a look at that point and that point, and then they're just taking the tangent vectors, and they're going to use the unit tangent vector, so that when we take a derivative down here of the tangent vector, we're taking a derivative of the unit tangent vector. So that kind of restricts all of the change to be rotational change. If the tangent vector is not changing in length, that takes away that degree of freedom. And the only thing changing then is the rotational, is the angle between the two vectors. So if you look at these two tangent vectors there, that's just demonstrating that there's a fair amount of curvature. There's a bigger angle between those two than if you look at this curve, where the angle between those consecutive tangent vectors is much smaller. So smaller curvature, bigger curvature. And the definition is simply going to be the rate of change with respect to s of the unit tangent vector. So that's our definition. We're almost never going to use that definition, though, so don't even write that down. That is dependent on a couple of things. You start with your curve, then you'd have to find t, capital T, and then you'd have to find capital T as a function of s, not as a function of little t. So there's a lot of work to get to this point. We're going to have a much more practical way to figure out our curvature. So you can think of it as the rate at which the unit tangent vector is turning, but in practice we won't use that formula. So we look at this a little bit more carefully. We all know from Calc 1 that you can divide top and bottom by a differential if you want. And so they divide top and bottom by the differential. And the denominator, ds dt, that's what v is down there, the speed, the length of v. That's ds dt. And then they have dt dt. This still is a pretty impractical formula. So let's keep on trucking. Don't even bother writing that down. Not worth it. This is the first form that might be helpful. We're still going to find another form. So here they've just sort of rewritten it a little bit so that it's the derivative of the unit tangent vector, speed, divided by derivative of r, speed, so magnitude. But again, you need t, which is a pain in the neck. Finding t is a hassle because you have to find v, and then you have to find the length of v, and then you have to do v divided by the length of v, and then you have to take its derivative. Right? Everyone follow why that's a total hassle? If we start with r, then we have to get v, and then the unit tangent vector is v divided by the length of v. V divided by the length of v, not v prime. And then after that, then we have to find t prime. Total hassle. So the only time we would ever use that formula is if somehow t was pretty easy to find. So we'll do one of those. But we're going to find even yet a better formula that's more practical. Because usually what we're given is r. So we would love to be able to find curvature using r and the derivative of r, or something simple, not something that's this kind of messy. So first, let's go ahead and do one like that, and then we'll come up with our new formula. So here we've got a circle of radius 2 centered at the origin. This is just sort of a heads up. We already kind of know. Circle of radius 2, what would we expect the curvature to be? 1/2. 1/2. So let's see if we get that with this formula. So let's just confirm that we're going to get what we think we're going to get. So the derivative here, which is the velocity, there's our velocity. And then our speed is the length of velocity. Pretty cool. That's pretty easy here. That's just 2. We know that that is a circle of radius 2. Its length is 2. So that tells us that our unit tangent vector, is going to be minus sine t comma minus cosine t. So unit tangent vector is v divided by length of v, r prime divided by length of r prime. And then we figure out what t prime is. All right. And then we have to figure out the length of t prime. So you get the point. It's kind of a pain to deal with this in this way. All right, so we're all the way down now where we've figured out what the length of t prime is. We figured out what the length of the velocity is. So therefore, we can calculate that the curvature for this circle is going to be 1 divided by 2. It's a circle, so of course the curvature is constant. Yeah?
Never mind.
Okay. All right, so that's kind of the traditional way that they think about curvature without using that formula. But again, you know, it's just a little bit of a lot of little details. So the curvature formula that I'd love to use is this one. This one is, I think, a lot easier to remember. It should look very similar to our formula that we've already used to find the distance between a point and a line, which we're going to review in a minute. The distance between a point and a line is v cross a divided by v. So that it kind of has that flavor to it already, and we're going to have to use the formula v cross a over v in just a few minutes when we start talking about acceleration and the components of acceleration. So that formula there is a much better formula to remember for curvature. V cross A over speed cubed. And we know that curvature is a number. So when we think about V cross A, we should sort of be keeping in our head that, oh yeah, it must be the length of V cross A, because we're trying to get a number. V cross A is a vector. And so we want to have a number, so we're going to take the length of V cross A divided by the speed cubed. This is especially useful when we're in 3-space. If you were to try to do what we just did up here with this example that looks really pretty darn simple, it's just a few trig functions, and you're starting to find t and t prime where you've got a whole bunch of trig functions, it gets really messy really fast. But with this V cross A method, it just keeps it a little bit cleaner. So let's go ahead and do the find the curvature using this formula. Why does that thing keep going there? I'm going to go there. Must not be oriented well. Okay, so still it's finding curvature is, there's always going to be some work. You're always going to be doing a cross product. You're always going to be finding a magnitude. So there's always going to be some work. But using that formula, it's going to be a lot simpler. So let's first figure out what our velocity vector is. And once we have our velocity vector and our acceleration vector, then we're good to go. So these are kind of two standard steps. If you've got R, figure out V, figure out A. Those are just two natural steps that you have to do almost any time you have a position function. So there's V and A. And notice that we now can cross them. And stacking is always best when you're doing cross products. We want the I component next, so we cross out the first column. We're going to get minus 2 cosine squared of t minus 2 sine squared of t for the first component.
Question.
Yeah?
So you have V cross A there. Didn't we talk about last time how a vector cross its derivative is always 0? Or is that just with the...
Only with a unit vector.
Okay.
So the condition, that's a great question, and we're going to talk about that actually on the next couple of slides. When you have a vector that's a constant length vector, it in its derivative will always be perpendicular.
Okay.
So the velocity vector here is not a constant vector. So the velocity vector is not a constant vector, so its derivative won't be perpendicular to it all the time. So we'll see that in a minute. When you take the unit tangent vector, capital T, and you take its derivative, it will always be perpendicular to it. So t and t prime will always be perpendicular to each other, but not v and a. So v cross A's middle term, we're going to cross out the middle column. We'll do opposite diagonal minus main diagonal, so we get positive 2 root 3 sine squared minus a minus is plus 2 root 3 cosine squared. And then the third component is going to be 0, I think. The third component, we have minus root 3 sine cosine plus root 3 sine cosine, so that's 0. And then this simplifies a little bit. If we factor out the negative 2, we end up with cosine squared plus sine squared, which is 1. And in the middle, if we factor out 2 root 3, same idea. So there's our V cross A. And let's come up here and find the magnitude of V, the so-called speed. So the speed will be the square root of the sum of the squares. Square root sum of squares. So we get 3 cosine squared of t plus sine squared of t plus 4 cosine squared of t. Oh, whoops, I got lost there. I started, oops. So the middle term should be cosine squared. Started squaring the wrong vector components. All right, so we're squaring these ones up here. So 3 cos squared plus cosine squared plus 4 sine squared. Weird dots, whatever. Yikes. So strange.
That's rough.
And that all ends up being 2. That ends up being 2. Okay, so the speed, what's that? Why is it 2?
Yeah.
Because 3 plus 1 is 4. So we get
Oh,
4
got
cosine
it.
squared plus 4 sine squared. Factor out the 4. Sine squared plus cosine squared is 1.
Okay.
Square root of 4 is 2. So what does that tell us right there? That tells us the velocity is constant for this. Right? Velocity is constant at 2. All right. So now we can calculate the curvature. So the curvature is going to be the magnitude of v cross a. So it's the magnitude of this vector. We can just write it out. Magnitude of v cross a. So it's the square root of 4 plus 12 divided by the magnitude of v cubed. So that's going to be 16. Square root of 16 is 4. 4, 8. So we get 1/2. Okay, so that'll be the curvature. That tells us, if we go back up and look at that object, if we have constant curvature, what does the object have to be? This has to be a circle in 3-dimensional space. Yeah. So if we go to that GeoGebra app and we plug that stuff in, we'll see that we have a circle in 3 space that's kind of tilted.
Does a sphere not have constant curvature?
Sphere curvature is defined on a circle.
You can't have curvature on like a.
Curvature of a, let's see, so if we're talking about a surface, yeah, we can't talk about the curvature because the curvature depends on the direction you're going. So if you imagine yourself on a surface, there's 360 degrees that you can go, and there'll be a different curvature in each direction. So we can't talk about the curvature of a surface unless, yeah, there might be some ways that if the surface is symmetric, you could define something like curvature. But, yeah, but in general, curvature is for a curve, not a surface. All right, so there's our curvature. Any questions on those steps? So I think that's the cleanest way to get curvature. Let's go up above and look at the one where we did it with the kind of longer method. And let me just write that on the board because we could do it with that one very easily also.
Wait a minute, what was the magnitude of v again?
I think it was 2.
Cute.
Oh.
That's the cube part.
So let's just take a look at this one. And you may say, oh, wait, that's 2-dimensional space. So is that going to be a problem? No. So let's figure out v. So v is going to be minus 2 sine t, comma, minus 2 cosine t, comma, 0. We'll just add a 0 component for z for a and v. And it's going to become really easy to cross these two because there's only going to be one non-zero component. 2 sine t, comma, 0. So we get that. So let's think about this geometrically. If we're in a 2-dimensional space, if you take v and a and cross them, you're going to get a perpendicular vector. So right away, you know, when you do v cross a, you know that you better be getting 0, 0. All right? So let's check. When we do this one, yeah, 0 minus 0. Cross out that one, we get 0 minus 0. So the only one that contributes is minus 4 sine squared of t minus 4 cosine squared of t. So this whole thing turns into 0, 0, negative 4. So the magnitude of v cross a is what? 4. So the magnitude of v cross a is 4. And the magnitude of v is 2. And then we cube it, and so we get 1 over 2. Yeah.
Did you just factor out a -1 at the end there?
Here?
So, like, yeah. How did you get your -4? Sine squared minus.
Yep,
sine?
factor out -4. So if you factor out -4, then you have sine squared plus cosine squared,
Gotcha.
which is 1. And then the magnitude of a vector that only has one non-zero component is just the absolute value of that component. And then we put magnitude of v cross A over magnitude of v cubed. So even with a two-dimensional situation, it's a little bit cleaner, a little bit more straightforward. Find v, find A, find v cross A, length of v cross A, length of v, and then use that formula. So that will be our curvature formula. All right, so let's talk about the unit normal vector. So this is usually called the principal normal. When you imagine a curve, there is more than one normal vector. Your unit tangent vector is always pointing in the direction of the orientation. So we'll just assume we're oriented this way. So those are unit tangent vectors. A normal vector just means perpendicular. So it's perpendicular to the tangent vector. And you say, oh, well, there's two of them, right? I could go this way or I could go this way. Well, when we talk about the principal normal always points inside. So that one is not the principal normal. The principal normal is always going to be a unit vector that points right inside. So it's going to point in the direction of the concavity. So those will be, oops, that's a vector, not a, or that's it. There we go. So this is the scenario that you should be envisioning in your head when you're thinking about tangent vectors and normal vectors. Unit tangent vector, unit normal vector, so that kind of thing. Then we're going to have a third unit vector that's called the binormal vector. If you take t and you cross it with n, it's going to create a third unit vector that's perpendicular to those two called the binormal vector. We're not going to use that vector a lot in this class, but in physics you would use that vector when you're dealing with torsion. Will?
So if you have a circle, then all the principal unit normal vector will be pointing to the center.
Yes, that's right. Mm-hmm.
That's the complete opposite of what I've been used to in 3D graphics.
Oh, interesting. They're not pointing to the center?
No, normal vectors always point outside.
So those are not principal normals then.
Yeah.
Those are normals, but not principal normals. So we'll do the same thing with surfaces. We can have normals that are pointing up or down.
All right, I'll
Okay,
wait
so
on
for a
this very
curve, the principal normal always points to the inside. And here is how we're going to find the principal normal. So we're going to take the unit tangent vector divided by its magnitude. Let me take the derivative of the unit tangent vector, divided by its magnitude, and this is going to be how we find the unit normal vector. We will never do this, though, this way. We are not going to do it that way. Conceptually, you are going to think of it this way. Find your unit tangent vector with as a function of t, so you've got your unit tangent, take its derivative, divide it by its length. That's a conceptual way you can think about it. But there's better ways. There's better ways. Well, we'll get to it in a second. So there's going to be, this is a reasonable way, but we'll see some other ways too. All right. So first off, it has to be understood why n and t are perpendicular. So there's just this assumption here that n is perpendicular to t. So we have to kind of justify that. And so let's just remember that t dot t is equal to 1. So t is a unit tangent vector. And remember that the dot product, if we look at the components of it, we are going to get the square root of the sum of the squares. And that's basically equal to t dot t squared. And so this will be the sum of the squares. We're going to end up with 1. You can go into detail on that if you're not 100% remembering that. So if you dot a vector with itself, you're always going to get the norm of that vector squared. So we can then take the derivative of both sides. So if we take the derivative of both sides, we're going to have first derivative second plus derivative first times second. Derivative of the right side is 0. This gives us 2 tt prime equals 0. This tells us that tt prime is 0. So therefore, t is perpendicular to t prime. So this tells us, that tells us why you can calculate the unit normal vector by simply taking the derivative of the unit tangent vector and getting something perpendicular. Because t is a unit vector, it's constant. It's a unit speed curve. Mm-hmm.
So a really quick algebra question.
Sure.
Should it be 2t times 2t prime?
Nope.
Okay.
Because here we have tt prime and here we have t prime t, and the dot product is commutative, so we have 1 tt prime plus a second tt prime gives us 2 tt prime.
Oh my gosh. Okay.
2 tt prime.
So pretty much if we want to find this principal normal, then all we have to do is dot t with t prime.
Yeah.
Well,
Yeah, that's one way you could do it. Good.
No, you.
Well, let's do it. We'll do it. We'll go through it here. All right. So we'll go through it the long way, and then we'll talk about some other ways. So t and n are orthogonal at all points. That just means that the dot product is 0 at all points. Principal unit vector points to the inside of the curve. That's the direction that the curve is turning. So here we have a curve in 3-dimensional space. Now in 3-dimensional space, there aren't a ton of shortcuts, unfortunately. 2-dimensional space, let's do the shortcut first, just so that I can convince you that there's an easier way if you're in 2-dimensional space. If you're in 2D, or what do we usually call it? R2. So if you're in R2, that's a terrible R2. So if we happen to be in 2-dimensional space, let's just make up some curve. Let's suppose we have t plus 1 comma t squared minus t. So we've got some curve in 2-dimensional space. Let's find n at t equals 2. So we're going to find the principal normal at t equals 2. So the first thing we can do here is find the velocity, find r prime. And we get that. And then we can find the velocity at 2. So the velocity at 2 is 1 comma 3. Everyone agree? We can find the magnitude of the velocity at 2, and that's going to give us the vector, or the number, square root of 10. So this tells us that our unit tangent vector at 2 is going to be 1 over root 10 comma 3 over root 10. So there's our unit tangent vector. Now we know that the normal vector is perpendicular to that. Do we need to do any math to find a perpendicular vector to that?
No.
We know that two vectors are normal if they dot to 0. So we can find a perpendicular vector by switching the coordinates, the components, and changing one sign. Correct? So n of 2, we have two choices. We switch the components. And we've switch the components here, and either we change this sign or we change that sign. One of those is the unit normal vector, the principal unit normal.
Isn't there supposed to be a cube somewhere in T?
Oh, for curvature there is, but not for this.
Okay.
For curvature, to find curvature, you do v cross a over v over speed cubed.
All right. So all we're doing here is just
Finding the unit normal.
Is it like either or, like you can pick?
So, how do you know which one it is? Well, what we would do is look at the graph of this and just figure out which way the curve is turning. So if we, I don't want to go through the details of that right this second, but if you were to graph this, you would let x equal this, you would solve for t, plug it in there, you get an xy curve, you graph the curve, and then you just look at that point and you just figure out, oh, should x be positive or should x be negative? Which one's pointing to the inside? What's that?
Is it going to be 0 in this problem? You take the derivative of t.
No. Remember that we take the derivative before we plugged in the 2.
Right, I just mean for n.
Yeah, you can't take the derivative after you've gotten your constant vector.
Oh, okay.
Right? So if you want to find n in general, you have to start here, find the length of this in general,
Okay.
and then take its derivative. Yeah, well.
So yeah, pretty much what you need to do is take take the second derivative of r, find and use to find the concavity at 2.
Yes, exactly. Exactly. So if we graph this, we'll see which direction the curve is turning, and then we can tell whether the principal normal should have a negative x or a negative y. Yeah, and you can look at the concavity of it. All right, so that's a lot easier if you're in 2 space. If you're in 3 space, 3 space is just messy. So let's go through one of these messier ones and feel the pain.
Feel the pain.
Feel the pain.
It's gonna be okay.
It's going to be okay, though.
Should we wait to write down until you're done?
No.
Okay.
No, you can feel the pain right away. There's no point in hesitating. No point in pausing. Okay, so there's our velocity vector. All right, unit tangent vector. So we have to find the speed. So the speed is the square root of the sum of the squares. So we have 16 cosine squared of t plus 16 sine squared of t plus 100. Take the square root of all that. That's going to give us the square root of 116. 4 goes into that because 4 goes into the last 2 digits. So that's going to be 2, and then 116 divided by 4 is 29, so 2 root 29. All right, so there's our speed. So this tells us that our unit tangent vector is going to be equal to 2 cosine of t over square root 29, comma, minus 2 sine of t over square root 29, comma, 5 over square root 29. So all we did there was take v and divide it by the length of v. So that gives us a unit tangent vector. Everyone agree? Because v is tangent to the curve automatically. So if we divide v by its length, that's going to squeeze that vector into a tangent vector, into a unit tangent vector. Everyone okay with that up to there? Okay, so that's t. Now let's take t prime. So t prime, we're going to get minus 2 sine of t over root 29. Then we're going to get minus 2 cosine t over root 29, and 0. So there's t prime. Now we have to find the length of t prime. The length of t prime square add square root. So we end up with 2 over square root 29. So then n is going to be t prime over the length of t prime. And that, lo and behold, gives us minus sine of t, comma, minus cosine t, comma 0.
Isn't it way easier and less tricky with numbers just to take the double derivative of the position vector and then divide by its magnitude? Because you get the same answer, but you don't deal with root 29.
That is only working in this case because of the geometry here, I believe. Say that again. So you said take the second derivative of r and divide it by the length of the second derivative of r?
Or yeah, the magnitude of that.
Magnitude of
So
r,
yes.
r double prime?
Mhm.
So that's only going to work here because we're in a lucky situation where A is perpendicular to V.
So pure coincidence.
Yeah, it's a coincidence here. And the reason they're giving us one that there is a coincidence is when it's messier, it's even worse. So, but what you said will work in this case because right here, yeah, because right here we know that this is, here we're dealing with a circle, right? V is due, if we looked at the geometry of V, it's a circle. And so that's going to be just a coincidence. Yeah, yeah.
Are they gonna turn out nice like that though?
Sometimes. Some of them are not nice. Some of them are really
Not nice.
unpleasant, unfortunately. Okay, so there is a unit normal vector as a function. Notice that it is a unit vector. If you take its length, square root of that, square root of that, or square root of square root of the sum of the squares is 1. So it's a unit vector. Okay, next.
Can you go back to that for a second?
Okay, so next we've got to deal with the components of acceleration. So acceleration is a vector that's going to be pointing into the concave side of the curve. And we're going to want to figure out the components of acceleration. So the applications here, there's lots of applications with acceleration. It's how you build a road so that when cars are going around the bend, they don't tip over. So you have to figure out how much force and curvature, how it all comes into play with the tilting of the road. So we have some sort of curve. We imagine the velocity vector. The velocity vector is going to be tangent to the curve. So let's just imagine that. And let's imagine our acceleration vector. So we're either accelerating or decelerating. So I'm going to draw it like that. So we're in an accelerating situation. So we've got that. So what becomes important is how much acceleration is contributing to the tangential direction and how much acceleration is contributing to the perpendicular direction. And so what we do is find the components of acceleration by looking at some stuff we've already done. So right there. Oh, that was great. Whew. Could have been worse. So what we are going to do then is rewrite the acceleration vector as, oh, I have it right up there. So we're going to write it as a constant times t plus a constant times n. So these are scalars that we're trying to find. These are the scalar components of the acceleration vector. So we're decomposing the acceleration vector, and the velocity vector, we can build our t vector. You can see the t and the n. If I put them in there, it's probably going to look really messy. But t and n, so let's suppose t is right there, n is right there. So whatever those vectors happen to be, there's our unit normal vector, there's our unit tangent vector. So we're going to write acceleration as a linear combination of t and n. Now, the cool thing is we've already done this in another context. We've already figured out the distance between a point and a line, and that's what this is representing right here. So the acceleration component in the normal direction, don't even bother with this formula. We're not going to use that formula ever. So that curvature times speed squared, we're not going to use that. This is what we'll use because we've already done it. So let's look at the picture and see if we can figure out why that formula is going to work. So if we take our acceleration vector and we build the implied parallelogram with the velocity vector, isn't the component of acceleration in the n direction, isn't that just the height of this parallelogram? Isn't this red vector right in here, if I can get to that red vector anymore? So this red vector that's in here, that one, right? That's right there. So the length of that red vector, that's the component in the n direction. That's really the height of that parallelogram. So the height of this parallelogram is found by doing v cross a divided by the length of v. That will give us the component of acceleration in the n direction. Everyone agree with that? So a sub n, right there. And a sub t, the other scalar, is right there. That is the scalar component of the projection of a onto v. And that's what this gives us. V dot a divided by the length of v. That is the scalar component of the projection of a onto v. So those two things we've already done, so we're just going to use those. We're not going to use new formulas because we don't need them. So v cross a over the length of v and v dot a. Pretty easy to remember. One's cross product over speed and one is dot product over speed. If you can't remember, if you know that one's cross product and one's dot product, and you're trying to figure out which one is which, can this one ever be negative?
No.
That one can't be negative, right? You have a magnitude in the numerator. That's never negative because the acceleration is on the inside of the curve. The principal normal is on the inside of the curve. That one's never negative. But if you have a decelerating situation, acceleration is projecting down in the opposite direction of v, that can be negative. If you're decelerating, then this is negative, and a dot product can be negative. So if you know one is a dot product and one is a cross product, and you can't remember which is which, you just remember that n and a are always on the inside, so they're positive, and the dot product, you can have a negative dot product, which is just a decelerating situation. So let's see if we can do it. So the vector function we have here, let's go ahead and figure out our velocity vector. And I'm going to put in an extra component of 0 because we are going to be doing a cross product, and we need 3 components. So we'll just throw in a component of 0 for the z component. Yeah?
Yeah, what would be the z component for r of t then?
0.
Okay.
Yeah, we'll imagine it a curve in the xy plane, so we can just add a z component of 0. And when we do the cross product here, v cross a, whoops, we're going to get, so first component looks like it's going to be 0. Second component looks like it's going to be 0, which will always be the case when you add a third component of 0 for v and a. Always the case. Third component is 2. So the magnitude of v cross a.
Wouldn't it be negative too? No, never mind. Worse than that.
Is it positive?
Yeah, it's positive.
And in the long run, because we're going to take the magnitude, it's not going to matter if you mix up your signs, but we should. But it is going to be positive too, though, because the main product is 2 and the other product is 0. All right, so now we're ready for Finding the magnitude of v. Magnitude of v is the square root of 1 plus 4t squared. So we get that. And what else do we need? We need our v dot t also, excuse me, v dot a. So we have v cross a. Now let's get v dot a. V dot a is 4t. So now we're ready to write our final answer. So a sub n, the constant component in the n direction is going to be v cross a's magnitude divided by v's magnitude. So there's a sub n. And a sub t, same denominator, except that we do v dot a in the top. So that would be the component of acceleration in the tangent direction. So for positive values of t, are we accelerating or decelerating in this case? We are accelerating because a sub t is positive. Because that means that the acceleration is pointing in the same relative direction as the velocity. Yep.
Did you say that again? You said the direction?
So a sub t is positive, which means that a and v are pointing in the same relative direction. They don't have an obtuse angle between them. So when we say they're pointing in the same relative direction, it means the angle between them is acute. So that means that we have an accelerating situation, not a decelerating situation when it's obtuse. Yep. All right, so the binormal vector. All right, so the binormal vector, we're not going to do a lot with the binormal vector. When you go on and if you go on to do complicated math or complicated physics, you will definitely use this vector. So the idea is that if you have a curve in three-dimensional space, the idea is that you can create a frame of reference on the curve that's based on the geometry of the curve. So you have your curve in three-dimensional space, you find t, you find n, you cross them and you get b. And there's a whole weird field in math called differential geometry where you can do something called coordinate-free geometry on curves and surfaces. Normally, we think of our curves as sitting in coordinate systems. But there's a whole bunch of math that you can do that has nothing to do with the coordinate systems that your objects are sitting in. So differential geometry, you study something called the Frenet frame, and it's basically Tn and b. But we won't do it in here. So to find b, pretty simple, just cross t and n. A simpler way, though, and this gets at the shortcut. You're talking to that, Blake, was that, who's talking about the a? Oh yeah, you were talking about the r double prime. This, to find the binormal vector, definitely a shortcut. Because you know that v and a are in the same plane, right? The velocity vector and the acceleration vector are coplanar. And if you cross those two, you're going to get something that's perpendicular to that plane. So perpendicular to t and n also. So a shortcut to find the binormal vector is just to cross v and a and then divide by its length. That would be a simple way to find the binormal vector. I will not ask you to find that on the test. So all you need to know is that you can find it. You can use the formula on your homework or your quiz if it shows up. If you're given the formula, you should be able to do it. And then also, I will not ask on the test unless I give this formula to you for torsion. Torsion, like curvature, is measuring the speed at which something is twisting out of a plane. So curvature is measuring the twisting in a plane. It's measuring the curvature it's measuring the bending of a curve. But then the curve can also twist out of a plane, and that's what torsion is measuring. We won't use it much in this class. If you have to find torsion, I'll give you the formula. That's probably the easiest formula to use. Yeah. Omar.
You were talking about the test. Just
Yeah.
interest. When is the test?
Oh, yeah, we'll review Thursday.
We don't have.
I mean Wednesday.
I was confused.
I'm not used to teaching Monday, Wednesday. We will. Yeah, we'll review Thursday.
Wednesday.
What she said. We'll review Wednesday. We'll review Wednesday.
Is there another quiz due online? This
Uh,
Sunday?
it's
The quiz is due on Monday. I
Monday
think.
night.
Yeah.
Yeah, Monday night.
Yeah.
Monday night.
After the exam.
All right, let's go ahead and do this problem. So let's go ahead and so here it says compute the binormal vector and the torsion. So again, these ones you're going to be given formulas if you have to do them. So the simplest way to find the binormal, let's go what we always do: find V and find A. You always find V and A. Those are. If you're confused, take the derivative twice. Take the derivative, take the derivative
there.
again, then cross them, then dot them. But we don't have a lot of options. We have our derivatives, we have our dot products, we have our cross products, and that's about it. Okay, so we've got our V, we've got our A. V and A. So V cross A has to point out of the plane. So V and capital T are tied together. A and N are tied together. And if you cross them, you go out of the plane. So this is pointing in the direction of the binormal. So let's find the binormal vector by crossing V and A. So our first component looks like 25 sine squared minus, oops, yikes. All right, so first component, 25 sine squared plus 25 cosine squared. That we can combine pretty easily in a moment. Middle component, 0 minus a minus, so plus, and that gives us, looks like 60 sine of t.
Wait, isn't it the?
So we cross out the middle column, we can do the main product minus the other product and then change the sign, or we can do the other product minus the main product, and that will give it to us. Third component looks like minus 60 cosine t.
Yep.
All right, so that is in the direction of the binormal vector. If we want it to be a unit vector, find its length and divide by it. Let's simplify this first. 25, 60, 60, minus 60, I guess. All right, there. Find the length of this vector. Square root sum of squares, so we're going to have 25 squared, 625, I think. And then 36 with 2 zeros. Sine squared plus cosine squared, I think we've done that enough to sort of see the pattern. So whatever that's going to be, the square root of 4225. Thank you. It's an integer.
So nice.
That's so nice.
Yay.
We can see that
I've
coming.
it a few times.
65. Okay. So now, quite simply, the binormal vector, the vector that's normal to both the normal and t, binormal.
Normal to the normal.
It's normal to the normal.
So which way is it going?
So it's t cross n direction. So
you're going up and then.
so if we're in the plane, if it just depends t to n. So roll your fingers from t to n. It's pointing in that direction.
Gotcha.
No more, no less. All right, so then 25 divided by 65, 5 goes into there, 5 goes into there, like 13 times. 12 13ths sine, and then minus 12 13ths cosine. So this should be a unit vector. 25 over 169 plus 144 over 169, that's 169 over 169, that's 1. So that's correct. That is a unit vector. That's our binormal. And then if we want to find torsion,
You have to take one more derivative.
we take the jerk, take one more derivative, the jerk. So when we look at this, formula, I want to point out one thing. Let's find A prime first. So A prime, which is R triple prime. I want to ask you this question. Is there any ambiguity if I was to write R prime cross R double prime dot R triple prime? Is there any ambiguity if I just took out those parentheses? In other words, is there only one way to do this, or could you do it in multiple ways?
Only one way.
Only one way. Because if you were to dot R double prime with R triple prime, you would get a scalar. And you can't cross a scalar with a vector. So when you see this is called the triple scalar product. There's only one way to do it. You have to cross these two first, because that forms a vector, and then a vector can be dotted with a vector to give you a scalar. There's only one way to do that, to evaluate that properly. And so that's our last step. So we've already figured out V cross A's magnitude, which is 65 right there. We've already figured out the denominator. All right, so
Well, it
that's
has to be squared.
so that's 65 squared. What's that?
Yeah. I
Yeah,
was just saying
65
so.
squared. You will just square that. So now all we have to do is dot the R triple prime with V cross A. Let's see,
Did we figure that out too?
can I get it out right there? Say that once again.
Yeah, we figured that out too, right?
65.
We can just dot it with that.
Yeah, we dot. Yeah, so we're gonna dot this one and that one. So we're gonna do V cross A dot A prime. And that is equal to 0, and then 300 sine squared and 300 cosine squared. So 300 sine squared plus cosine squared. And then you can write it.
2? No, I'm just kidding.
What's that?
You said 2?
2. 2. Everyone see that? So if you dot that with that, that with that, and that with that, everybody agree we get 300? 25 times 0 is 0, plus 300 sine squared plus 300 cosine squared. 300 times sine squared plus cosine squared is 300. So there is our numerator. So that tells us that our torsion is equal to that amount divided by 65 squared.
Which is just 4,225.
That one is 4,225. Oh, right, that's 4,225. And that should all simplify to something pretty nice, I think.
12 over 169.
12 over 169. So that's our torsion. So torsion is just a measure of how quickly something's turning out of the plane. But again, for B or torsion, if it's on the test, I'll give you the formula. It's not going to be a hard part.
When will you know if it's on the test?
Thursday.
Wednesday.
I mean Wednesday. No, I might not know till Thursday. It happens. Okay, so on on Wednesday, we will spend our entire time reviewing. To review, in the D2L site, there's a study guide, and that study guide just has lists of problems for you to take a look at. There's a lot of them. And I'll narrow it down on Thursday.
Wednesday.
on Wednesday. Oh my God. Next class.
You can't do it.
I have taught Tuesday, Thursday forever. I haven't taught Monday, Wednesday for a while. So, how many of you know how to use the study plan?
What now?
The study plan.
I do.
So,
I think I have before, but I don't know if it's.
so let me walk you through this. So, because this is the best way to go in and look. So, if you're looking at the textbook and it says, look at problems between 12 and 18. So if you come into the study plan, usually it defaults where it's not showing you the entire textbook, so click all chapters. And then if you come down to chapter 11, and let's suppose we want to do something in 11.7. Well, let's just click on 11.7. So these are all the problems that are in my math lab for 11.7, all those problems. So if the study guide says study problems between 11 and 17, then you're going to come and look and find 11, 13, 15, 17. So those 4 problems are then the ones that are related to that topic. So you can do all of them if you're hyper motivated, or just do 1 or 2 of them, or do at least 1 from each group, and that should be that should be enough to get you on the right track. So study plan, look at any of them. So on Thursday, come with any questions that you have as you're going through. Did I say Thursday?
Yeah.
No, I didn't.
Yes,
No, I didn't say it. On Wednesday.
Let's replace Thursday with Wednesday.
Yeah, you guys are going to come in on Thursday during my Calc 2 class. And be like, you said to come Thursday. So, yeah. All right, so do we still have a few minutes. We don't have to leave yet. We don't have to leave yet. We still have a few minutes.
Okay.
So let's do, one question that came up that it seems to be kind of hard is with the projectile motion problems. A typical test question could be something that has to do with finding the angles that you should use to hit a certain target. And so one of the hard things is that a lot of those problems in the homework, you have to use the quadratic formula. And we're not going to have a ton of time on the test to do quadratic formula, but you should be able to do it fairly quickly just to get your t values. I'll try to create polynomials that have pretty nice t values, but you need to be able to find your t value and then plug it in to get your angles. So when you're looking at those projectile motion problems, just make sure this formula you have to have down pat. So you need to know, and whether you build it from acceleration or whether you just know it is totally fine. And let's build it from acceleration just as a reminder because it's so important. But this one we are going to see, you will definitely have a couple of problems on the test like this. And it's going to be really important to be able to generate this equation pretty quickly. And the book uses, it's so confusing, but just remember that for their initial velocity, they use v0 in 2 different ways. That can be very confusing, so just be clear on that. And they use, for their R0, they use x0 and y0. So when you're building your velocity and your position, the typical way that we would do this is that we would build up and we would get u0 minus gt plus v0. So we've added the initial velocity vector to the integral of acceleration. And then we integrate again, and we get u0 t plus x0. And we get minus 1/2 gt squared plus v0 t plus y0. So that's going to be the most general situation. Most of the time, we're going to assume the origin. So most of the time, you can just shortcut that and say, okay, we're just going to deal with the origin, and we are going to convert. This is not very helpful with the u0 and v0 because it's more frequent that you know the angle and not the components of the acceleration vector. That's rare. Usually we say the launch angle is 40 degrees. So the final form, the form that you should really have down, is going to be this form for your position function. This would be at the origin, and we're going to replace the V naught and the U naught with the equivalent expression with alpha. So I took away the X naught, took away the Y naught, and then replaced U naught and V naught with their expressions in terms of alpha. So that formula is going to be really important to make sure you've got that down, whether you construct it or whether you memorize it. Either way, that's the one.
That's the one.
Do
Question?
you solve for, like, if we're looking for the angle, do you solve for alpha like I'm thinking that you
So usually if they say figure out the angle where you use the least velocity or whatever it is, you usually have a system. So they may say we're going to launch something at 1,000 feet per second or 1,000 meters per second. That goes in right there. That goes in right there. Then you have two unknowns. You have alpha and t. So then you have to use the x and the y. If they say that you are going to launch it and you want a range of 5,000 meters, you're going to set the x equal to 5,000 meters, figure out what the t is, plug that into the y, and figure out what the alpha is. So with all those problems, you end up with a system. You don't know alpha, you don't know t. So you have to use two equations with two unknowns to figure out what your alpha is by solving one of them for t and plugging into the other. So that's the typical layout. All right, we can stop there. Now you can leave. All right, see you all Wednesday.
You got it.
Woo! Wednesday.